Well, good afternoon, good evening, or good morning, depending upon where you are in the world, and welcome to today's webinar. I'm Charlene O'Hanlon, your moderator for today's event, and I welcome you. We have a great webinar on tap with some really interesting information, but before we get started with that, we do have a few housekeeping items we need to go over. First of all, today's event is being recorded, so if you miss any or all of the event, you'll be able to access it on demand. Following the event, we will be sending out an email that will contain a link to the webinar that you can access on demand. And with that, we'll go ahead and get started with today's webinar.
Hello and welcome to the webinar of Securing APIs at DevOps Speed, and I think it's about time we got started. So to introduce myself, my name is Erik Costlow. I focus on developer relations for contrast security, helping organizations secure software from the inside, understand where their vulnerabilities are, and how to integrate vulnerability detection and protection into applications. And over the years, I've done a number of different roles, starting out in my career as architecture and development, designing software that operated for a number of businesses. Then I moved on to do product management, taking over the what and why for different applications, helping design the requirements, ensuring that it met the needs, as well as consulting, helping people roll things out, deploy it in their organizations, and fully fit things to the business. Done a lot over the last 10 years in the realm of software security analysis for static analysis. And one of the most notable pieces of software that I've worked on was product management of the Java platform for Oracle. So back in about 2013, when Java had a set of security issues, instead of just watching that from the sidelines, I decided that was a good opportunity to engage that and see if I understand software security as well as I think I do, then I can go in and help with these cybersecurity issues. And we had about a 2-year shutout of 0 days, which was quite nice to manage. So the reason that I'm particularly credible to speak about developing APIs in a secure form is, number one, I've helped organizations secure a significant amount of software over the years through different mechanisms. I've also dealt directly in the runtimes that underlie software applications, specifically the Java platform, handling it when it went from the height of security problems of having a series of frequent exploits or a number of difficulty in order to bring it down to approximately 0 into the steady state that it is today, where it's a reliable platform again. I have also, if this is moving forward, done a significant amount in the realm of data center and cloud migration, helping organizations go from on-premise up to the cloud. And just for the record, I still do write a fair amount of software. I just write a little bit less of it now. Most of my work lately has been in the realm of microcontrollers, just because I think they're particularly interesting. And I want to start this out with the concept of a software puzzler taking advantage of an old koan, which is, if a tree falls in the woods and no one is around to hear it, does it make a sound? Well, if you want to have fun with someone who asks this koan, you can always say, yes, it makes a sound of one hand clapping, and just watch as they get irritated with you. But if we take this same koan into the realm of application security, what we can ask is, if software is hacked and there's no telemetry watching, does it still lose its data? And the answer to this is yes. If somebody still hacks an application and you're not watching, they're still in there, and they're actually in there for a lot longer because now they're able to just operate and you don't know about it. In that same vein, if a tree falls in the woods, it is still going to make a sound. It just so happens that you won't be able to hear it. Now, when we go to see what would actually be watching with that telemetry, I want to look at what different practitioners in the industry are calling the security CONGA-LINE, which is, as someone goes to make a request into an application, be they a normal user or an attacker, they tend to make that request in through the public API, your Swagger or Open API, or however you expose those endpoints. Then they go through, maybe they hit your web application firewall where you do DDoS. That goes into an application gateway to figure out where the request is supposed to go. Maybe you're load balancing it because you have a heavy usage. And ultimately, it'll make its way down to the server or serverless area before it hits the code that you wrote for that actual implementing API, at which point your API engages a different data source, a database, a NoSQL database, a file, and these are the things that ultimately consume the cloud spend. So if we want to look at what we're defending with these APIs, there's generally different perspectives in terms of what we want to work on. For public APIs, we tend to think about them more in the realm of authentication and authorization, fraud prevention, or just different bots and crawlers. But then when we have the implementing API, which is a lot of the code that we write, this is where things like vulnerabilities come into play. We can misconfigure them, or we can just have a little coding flaw with the way that we actually implement the API. Because this is where we actually go through to use our things like the custom code that we wrote, all the supporting libraries for our frameworks, any application server that runs it, and that underlying runtime, be it Java, Node, .NET, Ruby, or anything else. And I want to spend the majority of this webinar talking about the security of these implementing APIs because this is the code that a lot of people are writing. And the way that I want to do this is to go through and talk a little bit about DevOps in the beginning, how and why teams are going fast with DevOps, why development teams are operating this and how to fit with their cycles, security from the inside versus the outside, what is the difference of those, and then ultimately we have to run our applications. We don't just write code for the sake of writing code, so I want to talk about the deployment mechanisms of containers, virtual machines, cloud, and on-premise. So the reason that developers are operating with DevOps life cycles in the first place is to institute a faster feedback cycle where people can work on their applications and get effective feedback up as to what that application needs to do. And the reason that they do this is to meet up with business demands. We want faster time to value, faster time to market. We want to solve more problems faster. You also need to get customer validation in terms of why the application exists. A lot of people, they have a feeling for what they want, but you don't want to be in a situation where you spend a significant amount of time in a waterfall methodology building something only to realize that when the customer goes to actually use it, that you followed the spec and you did exactly what they asked for, but it turns out they wanted something else. That's a very dissatisfying feature to be in, so the faster feedback cycle helps you prevent that. Also, on team fulfillment, it's just a lot more fun to work on something where people give you feedback. Hey, I like this feature that you did last week. Hey, thank you for fixing that bug. It's just a lot more fulfilling to work on a team when you get feedback. So anything that we can do to decrease that feedback loop and make it faster is effective. Now, the main thing to look at for DevOps is the role of where is the customer. Because DevOps is not just about using a series of tools, it's not just continuous integration and rapid deployment. The goal is to have tools that support continuous feedback cycle so that we can get information about why the application exists in the first place and people's information and feedback as to how they want it to improve. So the aim of DevOps is that tools support the goal. The goal is not to just use a whole bunch of DevOps tools. It is possible to take a bunch of DevOps tools, and if you don't have this continuous feedback coming in, it's not exactly fulfilling the purpose of DevOps, which is to get that continuous feedback. Now, that said, there are a significant amount of commonalities of a lot of DevOps cycles, and the aim is always shorter deployment cycles. In a DevOps cycle, people tend to operate with deployments that are about 2 weeks or under. Some teams deploy multiple times per day, some teams deploy every week, some teams do deploy every 2 weeks, but the key is that it's a tight cycle. And then there's always a lot of tools that are common, wikis, integrated development environments, automated build tools, continuous integration, and then continuous deployment through things like orchestration and container management so that things can continually being pushed out into production where customers can see them. And then while customers are seeing them and people use the application, you have your telemetry and monitoring capabilities in the app. Now, the problem is if you just go fast and all you focus on is the speed of getting through this cycle, then what happens is you might take something that's absolutely beautiful of your application or this Ferrari, and all you do is you just end up crashing it into a pole, or you do something that's not very nice. Like, look at that horribly ruined car. What a work of art that's just been smashed and a very expensive mistake. So if you focus on speed without security, what you really end up with is a case of people being able to steal more data from you faster, which I want to be able to meet my SLA for my customers and deliver that value, but I don't want to be in a situation where hackers are able to go in and steal all my records in an appropriate time. If all I focus on is speed but not security, I end up having an application that can do something really bad really fast. And that's not exactly what I want, or at least I hope it's not what you want. Let's look at the way, though, that DevOps to solve the performance issues. And the way that they did that was not by taking everyone and making them a performance expert or sending them to training classes about how to produce effective performance tests, even though a lot of teams still do have performance experts who can tune things and understand laboratory tests. What it was by automating a tool at the right location to do the right thing at the right time. In this case, it's the realm of application performance management for performance that gives you feedback based on what's happening in the application as it monitors, so that you can have a continuous feedback coming back from the technical aspects to tell you where in the application something is slow. So rather than designing a test that may not simulate the real world, performance was solved by simply watching the real world through an automated tool. Now, the way that they do this is you take a performance monitoring agent, application performance monitoring, maybe a New Relic or an App Dynamics, and you just hook that performance monitoring agent into an application. Then you don't need any dedicated performance analysis tests. People just use the application as normal. The person, they might not even know that you're watching it for performance, but what happens is if the performance monitoring agent ever notices a problem, it tells you about it. It will say things like, your request response time has dropped above a significant threshold. You're taking longer to respond. Hey, this particular query is taking a little bit longer than it's supposed to. So what happens is you have the key information coming to you. Now, a valid solution for security is really to do the exact same thing and just cross the word performance off and write security. So if you want to do DevOps solution for self-service security, you start the application with a security monitoring agent. People use the application as normal, and tester doesn't really need to know that this is going on, and the security agent can notify you of a problem as it happens because it's able to watch the actual running API and understand fully what happens. So the key aspect of this is that the majority of the usage is safe, so the security monitoring agent really doesn't have to engage every single thing. It just tends to let things go, and it says, you're free to pass, the application can move on, and it only has to alert you when there is a problem. Now, this facilitates better working with teams because what it does is it lets DevOps teams move at their own pace, and now they can find tools that fit the way that they operate through that DevOps cycle, that infinity symbol at a rapid pace, with the opportunity to tell security teams what they can use in order to keep operating at this pace. And on a security side, it's nice to be able to let those DevOps teams operate at their own pace because that's really what they want to do. And the more you can hook in with their existing tools and methodology, the better they can do to produce effective security results for you so that you can move from a more engagement of having to go directly work with that team to monitor and oversee them and ensure that security is properly implemented in the cycle with the right tool at the right place at the right time. And the way that I want to cover this is to look at the evolution of DevOps and cloud operating at about the same time. And when we look at the NIST definition of cloud, what they've defined is that cloud has 5 essential characteristics. And for security, 2 of the 5 essential characteristics that are the most important are on-demand self-service and rapid elasticity. And the reason that on-demand self-service is important is those teams are going to be moving at their own pace. So just like they automatically buy and provision cloud resources on their own without talking to anyone, they need to be able to automatically grab security capabilities that hook in and produce data without having to engage somebody at the end or at a duration of each cycle. You can still have a person, but teams need on-demand self-service for all of the tools that they choose. Then rapid elasticity is this ability to scale up, scale down, scale out automatically without having to have someone go in and manually tune things. So a security solution that can fit alongside the 5 essential characteristics of a cloud is very likely to be adopted because it facilitates what everyone needs to do to deliver value to the business. When we look at this security self-service, the thing that we want to avoid is the concept of security gates, going through and saying, hey, you're about to release. Once you're ready to release, you got to schedule your penetration test that's going to be 2 weeks out, and then somebody's going to show up, they're going to attack the application, and you're going to have a lot more work to do. These teams need to be able to release because they're under intense pressures. So the more you have the security embedded along that DevOps path to produce the right results at the right time, the more effective you're going to be in terms of engaging those teams and giving them automation that automatically produces security results at the right time. And the key thing about this embedded security is when you can apply context of the application's code for what it actually does, you can be more accurate to get effective results to developers so that they can perform self-service operations. And the reason is when your security tools can automatically follow what the developers do for their DevOps cycle, they're more likely to be adopted in an effective manner. Now, Gartner's produced a nice chart of the DevSecOps pipeline, and it's just this same infinity symbol. You write code, you verify it, you put it into a testing environment, ultimately you release that, and then they've expanded in terms of the monitoring phase to have detection and prevention along the line. And ultimately, there's three key areas where we can go and engage applications, which is as the application is built and verified and run in its pre-production environment, and then in the production environment through the realm of runtime application self-protection, we want to be able to monitor how this application is actually attacked and differentiate when attacks are actually important versus when it's just nice to know that somebody's attacking us. Now, the ways that we can win this easily without complexity is we use a couple different techniques: software composition analysis, identifying older code with CVEs so that we know where we're vulnerable, using IAST or integrated application security testing, such that all usage of an application, even normal usage, is considered a security test. And then in production, we want to use RASP or runtime application self-protection to help defend against vulnerabilities and not have to look at the noise of understanding specifically when someone is attacking us. I want to be able to focus on when those attacks matter so that I can know where I'm actually vulnerable and I don't end up getting deluged with a significant number of alerts, false positives, and noise. Now, if we want to get oversight at developer speed, let's look at what people do and how development teams and security groups can operate together. A developer tends to work on an application, and as they work on an application, when you're automatically assessing it, you want to get security results automatically, both to the development team to fix it and to the security team to ensure that it's done. Then they both have the opportunity to look at those security results as they're generated automatically as someone uses the application. The security team tends to want to maintain oversight just to ensure that the security results are being generated, so they will verify things. And then ultimately, maybe both monitor for threats in production to understand where an application is used in attack. And finally, the key point is that touch points or gates or ways that the people would integrate and just automatically talk become an optional capability. So what we do is we enable an asynchronous communication where teams can work together using automation to do the heavy lifting of finding vulnerabilities and keying out what is critical. And the reason for this is that we want to stay fast and safe. We don't want to integrate roadblocks into someone's development cycle so that they can't release. We don't need to create any unnecessary gates that people are going to try to go around. And we don't want to insert delays into those DevOps cycle because the important part is to have continuous releases on an almost nonstop basis. And with that, I want to go and move forward and talk about when you integrate security, how is it different when you integrate security from the inside versus the outside? To look at specifically at the terms of the inside versus the outside, I want to look at what those mean specifically with the context just as words on their own. When I have something on the inside, I tend to look at the insider's perspective, the inside man, and that's generally somebody who has a handle as to what's going on and is fully aware of a situation. Now, compare this to somebody who's on the outside, which, generally speaking, they're not aware of what's happening. They're out of touch with things. In the case of an old song by Little Anthony and the Imperials, I'm on the outside looking in. And he wants to be, and he wants to be, and he wants to be back on the inside. It's a song, I think, from the 50s about a relationship breakup, because that person who's on the outside is lonely. Now, when we apply this to security, when we look on the inside, we're able to get results and security data from a running application using the context of what it actually does. When it comes time to defend an application, we're using that contextual knowledge of what the application is doing on the inside to defend the things that are actually happening. So our defenses are contextual. For example, we're defending a SQL injection in the SQL API. We're defending a file injection in the file API. But when you have something on the outside, you tend to be doing something like looking at the code, but not really understanding what that code is doing because you don't have the context of how it's actually run and put together. You're just kind of making a guess at how your flow graph, your data flow graph and control flow graph are going to look. When you go to defend an application, when you defend it on the outside using something like a WAF, the only thing that you're able to use is like a signature matching or a pattern matching based on how somebody has accessed the application over a network. You don't have insight on the inside as to what that application is actually doing, so your defense typically is not right because it's unaware. Now, the embedded security of an application, when you're able to take advantage of the running code, instead of one detection point that operates on a network between the user and the application, you're able to take full advantage of how the request goes in, enters an application, moves through all different layers of the code as it's pieced together, the functions, the libraries, the server, ultimately to the presentation tier, and goes back. You can see all of the assets that the application uses as a response to that user's request. So what you get is more visibility of what the code is actually doing and less noise because you are actually able to apply the context of each of these dots in the runtime because the commonality of the code is that the code is designed to run. Now, the reason that this API monitoring tends to beat things that are exterior defenses is when you're on the outside, you're something like a firewall that sits in front of the application, you only have one opportunity as a network to make a decision. But when you're on the inside, each of those dots that we saw earlier gives us an opportunity to make or improve our decision because we can apply contextual intelligence to that data flow as the application moves things together so that we can fully understand what's happening and either build and improve our detection and correction capabilities or to make a different operation and block it at whatever venue we want along that code flow path. Now, the automated tools on the inside, you tend to be able to look at things like the REST APIs, things like string concatenations as the data is used, if it does any encoding or decoding. When you're watching the actual data flow of an application to understand what it does, you can see each point along that code flow graph before the application actually goes through to access a sensitive operation. And what happens is you're able to report vulnerabilities in real time because you have the full context of what's actually happening. So even if that person is not going through and doing a dedicated security test, if they inadvertently do something that's a sensitive operation in an insecure way, you can inform those developers as they are making and testing the mistake so that they can understand and not have to do context switching to change their understanding and triage a whole bunch of results later that may be different. At the same time, if you're doing a penetration test on an application, maybe you attack the application in one way, trying one type of vulnerability. But if you're watching on the inside, you can go through and report to someone and say, you know, the attack that you tried didn't work, but you actually got a different type of attack. And if you'd looked for this one, you would have found it. But I'm going to tell you how the application is vulnerable anyways. So by being on the inside, you give a lot better contextual intelligence to anyone who wants to use the application. The way that we're able to do this hook on the inside is through a software process called instrumentation that lets you go and integrate into applications without any code changes. It's a very common thing to use because the way that software is created is a developer tends to go and they write source code. That source code gets compiled to an intermediate format that's often called bytecode. There's a tool that can do this called Apache Maven, or in the Java realm, you use the Maven repos. And then ultimately, when the code gets to run, it gets JITted or just-in-time compiled to a machine code. So this is the reason why the Java platform is called a hotspot system, is because it goes through and it JITs those hotspots a little faster in order to produce machine code that's optimized based on how the application actually runs. And through instrumentation, using the technique that's fully supported in the Java platform for over 15 years, it was introduced back in JDK 1.5 and is a part of the API specification through java.lang.instrument. What it does is it provides a hook made available through the -Java agent startup flag that during the JIT or before the JIT process, as you load your class files into the class loader, you have an opportunity to modify bytecode instructions and to add your own instructions into it. And anything that you do or engage with the application is fully protected by something called a bytecode verifier that is always present and always runs in the Java JRE to ensure what it loads. Now, anyone who's thinking about what are the impacts of this, is this going to have an impact to performance? Is this going to have an impact to compatibility? The impact on performance is very low. The reason is that classes are lazily loaded, so they're not engaged all the time or analyzed all at once. And when something that's on the inside goes to engage data, it looks at the memory that the application is already using. So it doesn't go out and create any extra additional elements. It doesn't have to go and do its introspection or build up the data in a representation. It just sits inside of the API calls that are already running, and it uses the same memory for what the application has already loaded. Now, the impact on compatibility is nil because Java has a bytecode verifier, so it validates all of that stuff anyways, and that's covered by a part of the Java language specification, in this case specifically the Java virtual machine specification, where I just took a screenshot of my Amazon purchase history, so you can see I had a wonderful set of beach reading back in August of 2014, which is when I was on the Oracle Java team and had to learn all the ins and outs of the Java platform. Now, the thing that security instrumentation does is it moves us from being on the outside where we don't have any context, and let's say someone attacks our application using a SQL injection flaw. If we're outside with no context and someone attacks our application, we'll look at that pattern match and we'll say, oh my God, this is a SQL injection. We had better alert everybody. I have fully detected that this is a SQL injection. And that might be right, but the thing is, when you're on the outside with no context, you don't know that the application itself is actually using MongoDB, which is a NoSQL database and doesn't use the SQL dialect at all. So maybe you've detected a SQL injection flaw, but it doesn't matter because you're not using SQL. Now compare this to something that's on the inside, understanding all of the APIs hooked in with the runtime. Somebody might institute a SQL injection call against, or a SQL injection attack against the application. So if you're watching from the inside, you can say, hey, you know what? I see this input coming in. It looks like a SQL injection attack, but this application doesn't actually use SQL at all. So I'm going to tell you you're being attacked, but I'm also going to tell you that you're being attacked in a way that's not vulnerable. So you as the security operator, or you as somebody who needs to worry about the application, you don't need to worry about this particular attack as much because it's not going to do anything. There we go. And what personnel problems does this role of instrumentation or being on the inside solve? It solves three primary problems. The first is alert fatigue, where you're constantly getting alerted and informed that there's a lot of attacks coming in. Because you can differentiate which attacks actually matter, you have fewer alerts that are brought to human attention for investigation. Another problem is a lot of the things that get through an application. While it might be easy to do a pattern match on certain aspects or to do anomaly detection of requests coming in, when you're on the inside, you can deal with things like deserialization flaws because you understand the context of what is actually going to be deserialized and how the class hierarchy would impact that. And you're not going to be fooled by things like someone changing their user agent or doing browser automation techniques using node frameworks like Nightmare. Also, when it goes to evaluate the application, you don't have to do tuning because things that operate on the inside can actually see what the code is doing. You don't have to worry about things like, we need to tune this particular part of the code to protect that particular asset. It's monitoring the running APIs so it can tell what the code is actually doing. So whereas an exterior defense might have difficulty with external facing APIs like REST or gRPC, when you're a part of the running code and the running application itself, you already understand that. And also not understanding when the application changes, if you're part of the application, you automatically know when the application changes because you're a part of the application watching it from the inside. So rapid release cycles don't really matter when you're on the inside because you're part of the thing that's being rapidly released. And anyone who wants to go look at things that get through exterior defenses that operate with no context, there's a very nice hour-long presentation. It's about an hour long of WAF bypasses that's done on InfoQ for someone who just attacks web application firewalls and gets through to break into the applications that they're allegedly supposed to protect. It's a very interesting hour of presentations of just how to get through everything. Now, integrated application security testing also tends to beat static analysis for various APIs because let's say we're working in an application where there's a large application and multiple development teams. So a member of one application development team says, I work on module A, and another developer who you can tell is on a different team because they have a mustache this time, they work on module B. Well, the way that these work with continuous integration systems is the continuous integration system will look individually at each module. It will go through and compile the complete results of module A, do an analysis of module A, and it'll say that's fine. Then it'll do an analysis of module B. It'll do a complete and thorough analysis of module B, and it'll say that's safe. But what happens is, because it never actually sees the code at a single time, what happens is you have a full report telling you that each module is perfectly fine, but you don't have all the code together at a single point because there's ultimately just an assembly job that takes the results of both modules and puts them together as the finally packaged application. So the key difference between interactive application security testing is that it evaluates things at runtime because all code is designed to run. So when you watch the application run, you see the whole thing because that's what it's designed to do. Whereas with other approaches, you'll tend to get just a pure analysis of module A, a pure analysis of module B, and you don't see the thorough results of those. Even though you have the source code to each, the source code never appears at the same time at the same place. Now, on the dynamic side, a lot of applications or a lot of penetration testers will go through, they'll try different attacks on an application. But if I'm just attacking an application from the outside, I might go through and I'm going to try one attack on an application, and maybe I go through and I want to do a cross-site scripting attack. Well, if the application is watching from the inside and bringing security results to me, it will tell me, you found one attack, you tried giving a cross-site scripting attack, but did you know we actually used that cross-site scripting name to create a file behind the scenes? So what happens is, by monitoring it on the inside, it will tell you what you actually found versus what you actually looked for. Another issue is as someone goes to attack an application, one of the security best practices or recommendations is that you don't return detailed error messages to a client. So you wouldn't give something like a stack trace, or you wouldn't tell somebody, SQL query failed. So the dynamic assessment or someone who wants to attack an application is limited if someone is not returning those detailed error messages. But when you're watching the application from the inside, you don't need to rely on information that comes back to the attacker because you can tell the way that your API call into an application engaged the code that underlies it to access different assets, and you can understand how it's vulnerable without key error data being sent back to a client because you're on the inside. There's also a concern of if I've actually tested the application. So one of the ways that Contrast addresses this is this concept of route coverage, which answers a couple different questions. The first is, what are the publicly accessible API endpoints in this application? And now that I know about these endpoints, have I actually gone through to test them? And if that answer is no, if you've been attacking an application for a long time and it turns out you've only tested 10 out of 19 routes, then you haven't really done a thorough evaluation of an application because there's a lot left. And even if you have, you always have the question of what did I actually find in this? So as I've gone through and attacked the application with different routes, what vulnerabilities have I found in relation to each route? Also, how has those routes changed? Because as developers work on applications, we tend to add additional endpoints or APIs to an application, and you want to understand if new APIs have been introduced that haven't been tested. Also, in the role of route coverage, I want to emphasize that a route is not specifically a URL because a lot of application frameworks tend to have what's called wildcard URLs, where in this case I have API orders, and then there's going to be a number at the end of it that's just an order ID that passes into a single function called check order that accepts a string. So if I'm attacking it from the outside, I might say, wow, I've attacked API orders, and I've evaluated order number 1 through a billion. The problem is, all you've done is you've tested the same single route over and over and over, but when you're watching the code path of what makes up those URLs and what the entry point is, you can actually gain effective coverage and understand that you want to test the entire application code rather than just assessing the same portion of the code over and over and over simply because the URL has changed as part of its wildcard pattern. And lastly, I want to look at the aspect of how code is designed to run and what those packaging mechanisms are. So I'm going to spend a little bit of time covering things like containers, virtual machine, cloud, and on-premise as applications are actually deployed. There's a couple common techniques that people use when it comes to deploy software and roll out the applications that they've actually used. And those three approaches tend to be containers, virtual machines, or bare metal servers where someone just SSHs to and operates with them directly. And the reason that I want to focus on these is this concept that nobody just deploys these elements for fun. Nobody goes and deploys empty containers or puts a virtual machine out there just for the sake of having a virtual machine. The entire point of each of these aspects is that they serve an application which serves a business need. So when I go to deploy a container, the key point is not to simply deploy a container, even if that's in Docker or Kubernetes or OpenShift or wherever I tend to put it. The key thing that I'm deploying is the application that's a part of the container. Or if I'm going to deploy a virtual machine, the key thing is what does this virtual machine actually do? And the thing that they do tends to be the application that's inside the container or the virtual machine or that runs on the bare metal server. Now, when we build an application, what we do is we take a set of components. We have a lot of components, the application, our custom code, the libraries, and we put them together. But one of the problems we run into is when one of the components that we use is vulnerable. What we assemble in that case is a vulnerable bundle because that vulnerability is now a part of the actual application of what we shipped. It could be our custom code, it could be a module or a library that we've incorporated, or it could be the way in which we've tied our custom code or brought certain modules together. But the key point is when a part of an application is vulnerable, just like you inherit the benefits of those libraries, you also inherit the vulnerabilities of those libraries. And we can approach this with the same realm of expecting vulnerabilities because even if we deploy something that's perfectly secure today, it might not be perfectly secure tomorrow. So what we want to do is to take the same approach of taking all the exact same bundles that we operate, our libraries, our frameworks, our runtimes, and we want to embed an internal security protocol as part of the application itself. And the reason that we want to do this is the ultimate artifact that we're going to get, it might still have a vulnerability in it, but the key aspect is this internal security monitor gives us the ability to make the application defensible because now something that can change the security behavior is a part of the application so we can adapt it without having to go through a special development cycle to patch the application and roll that patch through all of our testing and into production in a short time when we're worried about attacks. So if I embed security monitoring into an application, then the thing that I'm ultimately going to deploy can leverage that internal security monitor. And when we use this, we can use CI/CD or continuous integration, continuous deployment to place these security sensors in the right location at the right time. So what we can get is we go to build our applications, we can use that software composition analysis to figure out where we've incorporated bad libraries that have vulnerabilities in them. We can use our IAST, the ability to get everyone tested, all normal usage of an application as an effective security test so that we can watch that running code for security flaws without having to go through and engage somebody as a specialist penetration tester for every single release that we want to do, even if we're not changing a lot about the specific application. And then just the same way, when we go to deploy an application, we can automatically hook RASP or runtime application self-protection into the runtime so that that runtime can defend itself as it's out there operating in the wild, ready to scale up, scale down, or scale out. By being a part of the application, it's significantly easier to scale security when security is a part of the application. Now, when we go to engage applications, we want to focus on things that are common to all. And when we look at things that are on premise, in the cloud, a container, a virtual machine, or a bare metal, the thing that's common amongst all these applications is they all use the same runtimes. So, for example, a Java application is a Java application. A Node application is simply a Node application. A Python application is simply a Python application. And regardless of where I go to run this application, it's the exact same runtime, even though it might operate in a container or on the cloud or on premise. The key element that's the same is the runtime. The reason that I like to focus on the runtimes is that I like to take the approach that was popularized by Jeff Bezos back in the late 1990s, where you look at him there, he looks significantly different than he does today. He, as a visionary entrepreneur who has created one of the largest companies in the world, he said in an interview a long time ago that he's often asked with the question of what's going to change in the next 10 years. And if we look at software deployments, containers change, cloud changes all the time. But what Bezos focused on was the concept of what is not going to change. So Amazon is built on the premise that people will never say, I want my goods to be more expensive. I want to get them slower. What happens is people say, I want to get an item fast. I want to get it right away, and I want to pay a good, effective price, and I want to have a very large selection. So by focusing Amazon on those questions of getting items quickly, paying a low price, and having the ability to choose from a lot of things, that's something that's defensible in the same way that defending the software runtime is common and is not going to change for a lot of applications. So instead of chasing the thing that's going to be different, if we chase the thing that is not going to change and we secure it there, we now have a defensible point on which to build our security in our applications. And the reason that the runtimes support this is, again, what Contrast uses this instrumentation capability that is present in all languages and runtimes. .NET calls it the Profiler API. Ruby also calls it instrumentation, but it's more of a monkey patching. Same thing with JavaScript and Python. All of them support this concept of instrumentation to be able to adapt and get custom capabilities into a software program without engaging developers to make changes. You can do this through an auto instrumentation process. And when we have this auto instrumentation process and we become part of an application, we key off of this 5 essential characteristics of the cloud for rapid elasticity. Because when security is automatically a part of the application, as the application scales up based on consumer demand of how many people hit the application, security is a part of the application, so security scales up. If that activity rounds down and we have to decommission some nodes and decrease the number of containers that we use, security is a part of those, so security just scales down. So whether you're scaling up, scaling down, scaling out, when you have security as part of the application, you're automatically carried along with this role of rapid elasticity to be able to burst your capacity without human intervention. Now, the security inside an application also lets developers and security teams work much better together because it lets those development teams move at their own pace across this DevOps lifecycle. They can go ultimately as fast as they want. So on the security side, if you're always worried about the concept of how do I keep up with developers, they change things. Now, when you embed security into their process and you let them move across that DevOps or DevSecOps lifecycle as fast as they want, you can move from nonstop catch-up to more of an oversight plan. So the other benefit that this gives you is as you use technology in an application to automatically find and defend various security vulnerabilities, you can focus your mental efforts on things that cannot be done by automation, of figuring out complex attacks based on how you would actually attack the application according to its business logic, or something that simply requires human invention and human ingenuity rather than looking and going and finding your 5,000th SQL injection again. You can focus on things that give human value to understand things that computers cannot. Developers are also asked to support a lot of different capabilities. They're asked to, when it comes to an application, they're asked to write the code, construct it, do the architecture. Well, that application has to run quickly. So who does the performance engineering on the application? It's the same software developer. And if the application is insecure, whose fault is that going to be? It's going to fall on the role of the individual software developer. So rather than having them become an expert at multiple domains, we want to bake automation in a way that supports the software developer to produce high quality software rather than having them become a particular expert at every single domain. The tool that you can sign up for if you want to take advantage of this, there's a free Contrast Community Edition that's available at contrastsecurity.com/CE, where you can just take this agent, hook it directly into your application, and without engaging an SDK or without making any code changes, you just use a single environment variable. You can automatically hook security sensors inside of your application to gain contextual security intelligence based on what that application actually does. So you can figure out where your application is vulnerable and then protect it automatically in order to defend against vulnerabilities without having to deal with a lot of the noise that you would deal with if you were otherwise defending it with an external control on the outside. So Contrast operates on the inside, giving you that full contextual intelligence of what your application is doing and how it operates with data in a secure or insecure manner. Now with that, we've covered the role of containers, virtual machines, cloud on-premise, and how this security software has to actually run. So I want to wrap up the webinar, and we can do Q&A in just a second. But a couple key points to take away is on the security side, we need to let those DevOps teams set the pace because they're the ones that are operating across this DevOps cycle. They need to get fast response from their feedback cycles in terms of information coming back from the customer. So if we let them set the pace of how they operate through a DevOps cycle, we're going to get much better results and much stronger adoption of tools. And when we watch inside of those APIs, we have a much stronger ability to scale our security work with teams because we're actually watching and seeing what happens, and we can scale up, scale down, and scale out. And the more that we leverage automation, the more we can have humans do things that require human creativity, especially when it comes to security evaluations. Because we need development teams, if we want them to operate at their own pace and deliver key business value, we have to facilitate. All right, so for the questions, I've seen a couple questions have come in. So let me take a look at them. All right, we use a lot of legacy applications. Is this an issue for embedding security on the inside? So no, that's not an issue. Something can be a legacy application or it can be a new application. For Contrast, the way that works is Contrast goes inside of running code. So it doesn't matter if you wrote that application today, if you wrote the application yesterday, if it's a third-party code. Both legacy applications and current applications are handled in the same manner. All right. We don't want to be reliant on security experts or analysts to triage events and create bottlenecks. Right. So if you don't want to rely specifically on security experts, I think it's excellent to have security experts because you can have them running things like static analysis, like dynamic analysis. But what really helps security scale is something that can continuously assess applications and bring contextual results to you so that you can choose if and when to engage those security experts. You can still have them, but the key aspect is you don't need them on a regular basis because they tend to have a lot to do just the same way that developers have a lot to do as well. So I think by hooking security on the inside, it's a great way to have those security analysts, but not rely on them as a gating process. All right. And one of the other questions is, my developers don't have time to fix security bugs or to do security analysis. Yeah, so a lot of developers don't really have time to fix security bugs because they're asked to build new features into an application, or in some cases to rewrite and monitor an application. So the way that you can embed security from the inside is that developers can use like something like IAST or for contrast assess to find security bugs in their applications as they're creating them or actually just using and testing the code. They don't need a dedicated security expertise to do it. All they have to do is just hook an agent into the application and you can start producing results. And with regards to fixing those issues, there's a lot of issues that can be automatically defended through the runtime application self-protection because, for example, if you want to defend a SQL injection, you focus that defense on the SQL APIs, and you can do things like defending tautologies, figuring out if it contains 1 equals 1, or analyzing the parse tree of a SQL statement to figure out if user input that has come in, which you're watching, has changed in a way that makes the application vulnerable. And when you're watching it on the inside, you can actually see what the query is going to be, rather than if you're watching on the outside, all you can see is the data that goes over the network, and you never have an opportunity to see the query. So by being on the inside, not only can you more readily find issues, you can defend against them, and you shouldn't have to fix as much, so you can focus on the rewrites or the improvements of the application that you're actually trying to do in the first place. All right. Another question that's coming in. I think this is the last one that we'll take some time for right now. We can do some others via email if you want to send something in. We use a lot of third-party code during development. How can Contrast protect these dependencies? So the key part about all code, whether it's code that you write or whether it's code that someone else writes, is that that code is designed to run. So the logical place to defend this code is in the run time. So what Contrast can do is it can identify vulnerable open source components, which is often in a third-party code or things that you incorporate, and figure out if and how those are actually used by the application to prevent exploitation at runtime. So by using instrumentation, it's watching what actually runs. It's not just doing a file-based scan and saying, oh, you use this library, that library is vulnerable, therefore you're vulnerable. If you're not using the library because it comes into a transitive dependency, it's not actually going to have an impact on you. So what Contrast OSS does, that open source security, is it automates open source risk management by monitoring what the application actually does and uses so that you can pick out, do I have any vulnerabilities in this application through this third-party code? If so, where? And then am I actually using it? We also give you a lot of information in terms of versioning so that you can pick out how many versions you are behind, what the difficulty of upgrading is. So the key element is the relevance of, is there a vulnerability and do you actually use it? All right, and with that, I think we'll wrap up this webinar, and we can do a lot more Q&A over email, or if somebody wants to engage us in Twitter or anything, just feel free to do that. And by all means, feel welcome to sign up for Contrast Community Edition, where you can start embedding security into your applications within about 15 minutes from this webinar. All right, thank you very much, and have a nice day.